Let's look again at the averaging process that we introduced a segment or two ago. Here we have our original image of the Mona Lisa, and here we have the version of the Mona Lisa where we have applied an averaging over a 21 by 21 pixel input window. What can happen when we perform the average over a square window? It leads to an artifact in the image called ringing. It introduces very faint vertical and horizontal lines, and we can see a few above her lips and above and below her eyes. This problem arises because the pixels in the input window are different distances away from the center of the window. In particular, this pixel here is a distance of 2 away from the center of the window, where this pixel here is a distance of 2 root 2 away from the center. That's a value almost 3 pixels away from the center. And the result is that the average is unduly influenced by pixel values that are a long way from the center. And we say that this operation is not isotropic. That means that it has different results in different directions. It's not symmetrical. Ideally, what we would like to do is to extract a circular region of pixels. We'd like to take all of the pixels that fall underneath this circular disk. But the problem with this is that the disk doesn't fully cover all of the pixels. Some of the pixels around the edge, particularly the ones in the corner, are only partially covered by the disk. So that involves us taking a fraction of a pixel. Let's look at a way that we can do this. And the way we do it is to apply a weighting. So let's zoom in on this circular region that we've created, and it's a circle with a diameter of 2.5 pixels. And we want to take all of this pixel because it's fully covered by the disk, and we want to take all of this pixel because it's fully covered by the disk, but we only want to take a fraction of this pixel. We want it to have less significance or less weight in the average that we're going to compute. So what we can do is to compute a set of weights. For pixels that are fully covered by the disk, the weight is equal to 1. But if the disk only partly covers the pixel, then the weight is less than 1. And we can see that there are some pixels 98% covered by the disk, and in the corners we can see that there are some pixels that are only 14% covered by the disk. This matrix then represents the influence that the different pixels within the square window should have on the resulting average. How do we use this weighting matrix? Well, what we're going to do is to take all of the pixels from the input image, and here's an example of a set of pixel values, and we're going to multiply all of the pixels within the window by the weighting matrix. And this is an element-wise multiplication, sometimes called a Hilbert multiplication. So we take corresponding elements from these two matrices, multiply them together, put the result into the corresponding element in the output matrix. So over here we have the pixel values from the original image, but we've multiplied them by the weighting matrix so that the ones in the corners have got a lower value, less able to influence the resulting average. Now we will compute the sum over this product, and it's the product of all of the pixels in the input window, which we denote by W, and all of the values in the weighting matrix. And I'm going to now to refer to that weighting matrix as a kernel. A kernel is a term that's commonly used in image processing. We're going to compute the sum of the element-wise multiplication of these two small square images, and the result is what we place into the output image. So our function f of w is equal to the sum of the element-wise multiplication of the input window and the kernel. Consider now that I have an input image where all the pixels are uniform and equal to 1. If I applied this kernel to that image, the result would be that every pixel in the output image would have a value of 19.6. Input image, the values are all 1. Output image, the values are all 19.6. We can get around this by applying a scale factor. And the scale factor is determined from the sum of all of the elements within the kernel. If we divide the kernel by the sum of all of its elements, we have a normalized kernel, and if we apply this to an image where all the input pixels have got a value of 1, the output image will have all of its pixels equal to 1. This is a normalized kernel. So typically we try and compute a kernel that has got a scale factor of 1. So the simple averaging that we looked at right at the beginning of this lecture, we can also think of it as a kernel. In fact, it's a very simple kernel where all of the elements in the window are equal to 1. So here's the example for a 7 by 7 window. a 7 by 7 matrix of 1s. We divide it by 49 so that the overall scale factor is equal to 1. So this is a fairly uniform way of dealing with spatial operations. They can all be represented by a kernel matrix. And in the MATLAB toolbox, we use a function called iconv. We pass in the image, in this case the Mona Lisa image. The second argument is the kernel matrix. In this case, it's a 7 by 7 matrix full of 1s divided by 49. The function 1s is a built-in MATLAB function. Another kernel that's very commonly used in image processing is the Gaussian kernel, named after the very famous German mathematician Carl Friedrich Gauss. You have perhaps encountered the one-dimensional version of this function before. It's the normal distribution that we see in statistics. This function has got a very simple and elegant analytic form, and if we plot it in 3 dimensions, it has the appearance of a gentle hill. If instead we represent this function as an image where brightness is proportional to height of the function shown over on the left, we have an image that looks something like this. It's bright in the middle, and we can see that the intensity falls off uniformly in all directions. This is an isotropic function, and the weight decreases as we move away from the center. In the MATLAB toolbox, we can compute this kernel using the function kgauss. The first argument is the standard deviation, the symbol sigma on the left, and the second argument is the half width of the kernel. In this case, the half width is 15, so therefore the full width is 2 times 15 plus 1. That's a kernel that's 31 by 31 pixels. An important parameter of the kernel is the standard deviation, the symbol sigma, which appears twice in the analytic expression. It controls the width of the kernel. So for sigma of 2, we see that it is a very tall, pointy peak. For sigma of 5, it's much broader. For sigma of 10, it's broader still. The area under the Gaussian function is always 1, so as it gets wider, it becomes less tall. An important consideration when we use the Gaussian for image processing is what size should the kernel be. The kernel needs to be big enough to hold the bulk of the Gaussian, and that clearly is going to depend on the standard deviation. So a pretty good rule of thumb is to make the half width of the kernel equal to 3 times the standard deviation. Let's create one of these Gaussian kernels. I'm going to put it into a variable called k. It's the kgauss function, and I want it to have a standard deviation of 5, and I want it to be in a window with a half width of 15, so that will actually be a 31 by 31 kernel. There we go, we've created a 31 by 31 matrix in the workspace which contains the Gaussian kernel. Now I can display this as an image, and there we see it is essentially a disk. It's bright in the middle, it's got a high weighting to values in the center of the window and lower weighting for pixels that are further away from the center of the window. Now I can create in a new figure, and I can look at it in a different way. I can look at it in a 3-dimensional way by creating a MATLAB surface plot, and there we see the Gaussian window, very distinctive shape, tall in the middle and with decreasing values as we go away from the center. Let's apply this kernel to our standard test image. So we'll load the Mona Lisa image. I'll create a new image called S for smooth, and I will correlate it with kernel. There we have created the output image, and I can display that, and we can see that the image has been smoothed. We might also say it looks a bit blurry, it looks like it's lost some resolution. What we've done is smoothed out the very fine scale detail and left just the coarse detail in the image. And you can see that for the case sigma equals 2, we have a relatively small kernel size. For sigma equals 5, we have to use a much larger kernel.